Hi everyone. So good evening. Thank you all for coming. Now we're going to be talking about LLM Inference 101. It's an intro to understand what LLM Inference is, how we do it, the challenges that inference rises, and let's jump into it. So my name is Asaf Gardin. I've been working at AI21 for about a little bit over 2 years. I work at the Inference team in the company. Before that, I've worked in several startups. I've worked at IBM. That's pretty much about me. Today I do Inference at the company. And what is our agenda? So we're going to talk about a little bit what Inference is. We're going to talk about the key challenges of Inference. We're going to talk about vLLM as the solution for Inference. A little bit about some of the features that vLLM offers. And at the end, we'll have time for some question and answering. And if not, then we'll talk about it later. You can grab me at the end of the lecture, and I can answer some questions. Okay, so I'm going to talk about a little bit on the high level of what the how the flow of an inference. So we're going to talk about we're going to start with a simple prompt that the user sends us. Say the Paris is the city or anything else. It goes to the inference engine. And it goes through a component called a tokenizer. The tokenizer has several algorithms. I'm not going to talk about which algorithms the types of tokenizers has. But let's say it's a black box. It takes the text, creates tokens. The tokens are numbers that the model can understand. It's a language that it can understand. The model does whatever it does, creates logits. The logits go through a softmax function, and then they create probabilities, and then the model can really take the most likely token per generation token that it chooses, that it generated. So what are the challenges that Inference has? So today, Inference needs to be able to run on all sorts of hardware, from GPUs that have multiple types of GPUs, from CPUs, from TPUs. We need to be able to run inference on all these hardwares, and we also need to be able to run more than a single request at a time. Meaning, we need to have a batch size of larger than one, so we can handle as many requests as possible, return them as fast as possible to the user, to all the users basically, and that's the main thing. And some of the other key challenges that we have is how to efficiently schedule all the requests into each forward pass of that request, and how to manage the KV cache in a smart way. That's because the KV cache we'll see in a few slides is very, very intense in memory. And another one thing is that we always need to keep the GPU utilized, meaning we don't want to have idle time for the GPU and have them always working. Okay, so why is it a hard problem? This image was taken from AnyScale's blog, by the way, which are here tonight. So why is it a hard problem? So an LLM, as we discussed, we can look at it as a distribution function, meaning that the model needs to predict every token based on the token prior to it. It's an autoregressive method. A single request can take multiple passes through the model. It's not just one call to the model, and the model takes the request, generates a token or whatever amount of tokens with one go, and then back to the user. Every time we generate a token, we go through a whole forward pass in the model. Every generation can last several seconds, can even last minutes for very large requests. We go through through thousands of forward passes through the model. That is very, very intense in the memory. And here you can look at how it looks of a simple toy example, where we have a request with 3 tokens. That's the yellow boxes. So we have a prompt of 3 tokens, and every time we need to generate a token, we go through one iteration in the model. So we have 1 token, then 2 tokens, and 3 tokens until we get to an end of sequence token. And that took us all about 5 iterations in the models. Okay, so why is it a hard problem? So one of the things that, so the way it was before vLLM or any other inference engine before LLMs really, we had something called dynamic batching, where the server had set a time window, and all the requests that had come through that time window to the model would get handled. And it doesn't matter on the length of the request, the length of the prompt, I mean. So you can say, and that means that the long prompts dictated how fast how fast or how slow the response would be. So that means that if we have a short request, you can see the second row has a request with 2 tokens that need to generate, let's say, 7 tokens, and the third request that came in with it, it's only generate 1 token. And you can see that the third request ended very quickly with 1 token, but all the requests that came with it now need to wait for the longest request to end. That's a very, very inefficient way to do this. And so what we have today in all the inference frameworks is something called continuous batching. And what that means is that we don't collect the requests on the request level in the server, but on the iteration level. What does that mean? It means that we start handling requests as they start flowing into the server, and the second that one request finishes, we return it to the user and start handling more newer requests. We check on every time we finish one request, we check if we can handle more requests at the same time. And if we do them, we just start handling them without waiting for the longest request to start to finish. One more thing that we need to go over is a little bit in a high level on what KV caching is, because that's one of the main things that vLLM had to solve. Now, KV caching, without getting into the bits and bytes of everything about it, when we do attention, we need to calculate a few vectors, sorry, and the flow of that is basically when a new request comes in, we calculate and store the initial KV cache vectors of that prefill request of the prompt. Then once we start generating tokens for that prompt, we retrieve the KV cache and add the new values of the current tokens to the KV cache. We calculate the attention using the cached KVs that we just stored, and we update the KV cache with the new KVs, and we'll loop until we finish the entire generation of the request. Okay. We can see how it looks a little bit more visually per iteration of a token. So the upper one is without cache, the bottom one is with cache. So the first iteration is pretty much the same. The second one, you can see that at the bottom, we don't need to go and calculate the query tokens for the key tokens or the value tokens of the previous token. We simply use the same K and token and the K and V's of the previous tokens because we cached it. You can see it in the next iteration and so forth. And one last thing about KV caching that vLLM had to solve is that KV cache is very intense. It's very large in memory. It's not very efficient. So we can see here that we have an example of a 13 billion parameters model on an instance that's A100 with 40 gigabytes of GPU, and that model takes about 26 gigabytes in memory. That's 65% of the model, and the KV cache could get for one request to about 12 gigabytes in memory. So just one request. That's almost all of the entirety of the GPU. And so that just shows you how much inefficient KV caching could be. Okay, so now we've come to vLLM, the fastest and easiest to use open source model, Inference. vLLM is one of the most popular LLM inference engines currently. They have over 60,000 stars on GitHub. They have more than 800 PRs per month, over 1,000 contributors. We contribute to vLLM currently, and we always had support for Jamba, and we'll talk about it at the end of the presentation. So yeah, so what did vLLM bring to the world? So when vLLM first came out with their article and with their inference engine, they came out with something called PagedAttention. PagedAttention's main goal was to handle the way KV caching memory management is. So before the PagedAttention, the way KV caching was handled and the memory management is that every request for every request that came into the inference engine, we would allocate a long continuous block in memory, And that was very inefficient. And why? Because that was the way to create a lot of fragmentations, a lot of small bubbles in memory. And then even when we did have enough space to get more requests and handle more requests, we couldn't, because those requests was just, those bubbles in GPU memory, in the GPU were not long and continuous enough to handle them. So PagedAttention came to solve that. And what it did was they basically chunked and created small pages for in memory instead of one long ones, and they took that inspiration from the way that operating system virtual memory management is. So they divide the KV cache into small pages instead of long continuous blocks that allow them to reuse and swap memory pages across sequences as they grow or finish and avoid fragmentation. And we can see how that looks. That's an image from vLLM's article. You can see how we have 2 requests here, and how for every 4 tokens basically is mapped from a logical memory to a physical memory. You can see how the first 4 tokens of request A go to block 1. The next 4 tokens they go to block 7. They're not continuous in memory, but they're scattered all around. Sorry, and that was more efficient to handle, and that didn't create fragmentations. And if it did, it was just very, very small. Okay, that was just an image to show you how another way of how that might have looked. There's a token. Once the token's KV cache was generated, it would look where it had enough, where there's an open block to be stored, and it would just go and store it there. Okay. So we've gone over what vLLM brought to us, and the main thing that they've built their inference engine on. The next thing, and now we're going to talk about a little bit about some of the features that vLLM has. These features aren't necessarily just in vLLM. Okay. Also, PagedAttention is already part of every inference engine out there, probably. So we're going to talk about some of the features that they have. One feature that's crucial for inference today, and I think every inference engine wants to have it, and every model wants to use it, is automatic prefix caching. And what it is simply an idea of caching the KV cache. So what does that mean? So here we have an example of 2 requests that are sent to the engine. One request says, what is the capital of California? Now we calculate the attention for request A, and then when request B comes in, we can see that the prefix of that request is exactly the same, meaning we don't have to calculate the attention of that request because we've already done that in the previous request, and we now just use the KV cache of request A, and we now only calculate the attention to the token or word friends, and that could save us a ton of time. A more realistic example would be a RAG or a multi-turn conversation, where we have a lot of context and repetitive context. Second thing that we have in vLLM, and again, other frameworks, but it's crucial for inference, is quantization. We basically need to compress the model precision from precision X to precision Y. Usually it's from a higher precision type, like FP32, FP16, to something that's a little smaller, like FP60, int8, int4, FP8. And the main goal of quantization is to make it to make the model smaller and faster and cheaper to serve. Now we have a few methodologies, a few quantization types. Sorry. The main one is weight quantization. Basically, we take the weight of the model and we quantize it. What does that mean? And if we have a model that's 100 billion parameters big, that's 200 gigabytes in memory, by quantizing it from bfloat16 to FP8, for an instance, you cut it by half, and now you can feed the model on different types of GPUs, cheaper GPUs. Serving the model is also faster because the model's precision is lower. We have KV cache quantization, which is essentially the same thing, but we only reduce the KV cache storage type, and that could lead to faster attention calculation because we do it on a KV cache. And we have something that's a little more, that doesn't happen very often, and if it does, it happens usually with weight quantization, is just the activation quantization, and that just allows a faster matrix multiplication and communication between the GPUs. So the advantages of quantization is improving latency and throughput. Because we lower the precision of the model, we can now handle more tokens under a higher load. You can see from the graph here that we have for requests per second on the x-axis and for the time per output token, meaning how fast we generate tokens, on the y-axis you can see that for about, and lower is better here. So you see that the blue line lets you handle more requests and also generate more tokens with just quantizing the model. One more thing, well, a few more things we have is reducing the deployment costs, because we're now gonna be serving our model on cheaper GPUs. And another cool thing that a vLLM offers here is that it has a runtime and static quantization options, meaning you can, and we'll show an example of how that looks when serving a model with vLLM, but vLLM allows you to also give them like the static weights of a quantized model and serve it with special kernels that they have on how to serve the model. And another thing that you can do is also quantize the model in runtime. And you can tell the model, you can tell vLLM, hey, take my model and quantize it to this. And I'll show an example of something that we've also developed in the company later. The main disadvantage of quantization is the minimal accuracy loss that you could have. Every model could have different accuracy loss. Some models are quantization-based training. Some models are just not as good for quantization. So I always recommend people to, when they decide to quantize the model, always test the quality later. Okay, and one more thing we're going to talk about is distribution inference. Now the guys here at Ray can probably tell you more about it than I can, but I'll talk about it briefly. So why do we need distributed inference? So as models get bigger, one GPU could just not be enough. So models need to be able to run on, some models today are very, very large. DeepSeek, Jamba large that we have here in the company are very large models. They can't run on a single GPU, and some models can't even run on a single node. So you need to be able to run to run those models on multiple GPUs and multiple nodes. So one of the main things we have is called tensor parallelism. Essentially, we shard the model weights to the amount of GPUs we want to run on, and that allows us to to split the model on the amount of GPUs and basically fit our model on several GPUs when it can't just fit on a single GPU. The downside for tensor parallelism is not slow communication, because it needs to always summarize but sum the values of the results, and that's a lot of iterations, a lot of operations between GPUs. That takes a lot of time, and it's not very efficient, but it does the job. One more thing that we have is called pipeline parallelism. Essentially, when a model can't fit on a single GPU or a single node, then we resort to something called pipeline parallelism that allows us to run a model on different nodes. Another thing we have is called data parallelism. So what this does is I think the simplest one to understand. We simply replicate the model weights on every GPU, and every kind of GPU turns into a small micro server. And we have a request router that kind of load balances the requests per GPU, and that could really increase throughput when we need to handle a high load, and so on and so forth. Okay, Yuval, we have time?
Yes.
Okay. So Jamba. So here at the company, Jamba, as Yuval said, is a hybrid model. It's both attention and Mamba, and Jamba wasn't implemented in vLLM. When vLLM first came out, it was attention. It was it had only support for attention models, and they didn't even have Mamba. Mamba was also relatively new concept at the time, and we needed to add Mamba, support for Mamba models to vLLM because they didn't have that. And once we added support for Mamba in vLLM, we were also able to introduce Jamba to vLLM, which consolidated both architectures. That's just a snippet from the code that we have added. We also, we keep contributing to vLLM to this day. We now added V1 support, if you guys are familiar. We added automatic prefix caching to vLLM. One more thing we did add, which I said before, is a new way to quantize Jamba, and you can also use it for other models as well. It's a quantization called experts int 8. Okay, so how do you run Jamba large on vLLM? So Jamba large is a very large model, and as the name implies, and it's about 801 gigabytes of memory. So as you can see, it can't fit a standard GPU, 8 GPUs, not 8 GPUs, sorry, standard instance. And here I have an example of how to serve Jamba on 8 GPUs H100 instance, where each GPU is 80 gigabytes in memory, and so that sums up to 640. But as you can see, that still doesn't fit, right? Jamba is still 160 gigabytes larger than that. So what do we do? So the first thing we do is quantizing Jamba. So when we use the new quantization that we've added for Jamba in vLLM called expert ints, we quantize Jamba from FP16, which is the D type of the model, to expert int, which is now 400 gigabytes of memory. So that's already great, because now we can fit Jamba on 640 gigabytes of GPU memory. Second thing is we need to use tensor parallel size. Tensor parallel, and why? Because one GPU is 80, and we need to run it across more than one GPU. So we're going to use tensor parallel, and it's going to be 50 gigabytes of model on every GPU. So that's great already. You can see the command on how that might look. And one more thing you guys might add to Jamba is to enable prefix caching, because that's always great. It's a new feature in vLLM, by the way. It only came out just about now. And all of these things should allow you to run Jamba large on H100. And that's about it. If you have more questions on how to run Jamba, on how to use vLLM, or anything that I've just discussed, or any of the other features that vLLM has and that I didn't talk about, you're more than welcome to grab me afterwards. And that's it.